Welcome back. Now that we understand how to take derivatives of expressions, we're ready to learn about implicit differentiation. When we differentiate a function where y is solved for, we are differentiating explicitly. Sometimes solving for y is difficult, inconvenient, or impossible. So differentiating an equation where y is tangled up with other variables is called implicit differentiation. With both explicit differentiation and implicit differentiation, the goal for both methods is to find dy dx, or the derivative of y with respect to x. Take a look at this expression. Would we have an easy time solving for y so that we could use our explicit methods to find the derivative dy dx? Probably not. Implicit differentiation makes it a lot easier to complete this task, because we get to leave y tangled up with the other variables, in this case x. Let's go through the process of implicit differentiation. As I go through these steps, you may not fully understand what I'm talking about right away, but it'll become clear once I start doing examples. In the meantime, you may want to jot down these 4 steps on a piece of paper so that when you're working through problems, you know what you're supposed to do to get the job done. Now, every implicit differentiation problem begins with an equation that's given to you that relates x and y somehow. So step 1 is to take the derivative of both sides of this equation with respect to the independent variable. The independent variable will be found in the denominator of the rate you are asked to find. So if you are asked to find dy dx, you see the x in the denominator, you should be finding the derivative of both sides with respect to x. Now, the equation that you get when you take the derivative is called the differential equation. You're going to manipulate this differential equation so that all the terms that have dy dx are on the left-hand side, and all the terms without dy dx are on the right-hand side. Now, the reason you wanted to collect all the terms that have dy dx together is so that you can factor out dy dx from all of those terms that are on the left-hand side. This new result will have dy dx multiplied by some quantity, and then the right side should not have any dy dx's. So to find what dy dx is, we isolate it by dividing both sides by the other factor. At that point, we have dy dx solved for, which is the goal of the process. Let's start with a very basic example that shows what is going on with implicit differentiation. It'll make a good point to show that if we do the problem explicitly and implicitly, that we're going to get the same result. So explicit differentiation means that we need to have y isolated first. Since they gave us that y squared is x, so to solve for y, we can raise both sides to the 1/2 power, and we'll get y equals plus or minus x to the 1/2. Now that y is isolated, we can take the derivative explicitly, which means the methods that we learned before this new topic. So the derivative of y is dy dx, and the derivative of x to the 1/2 is 1/2 x to the negative 1/2, and we'll keep the plus or minus in front. That is considered done. We were asked to do it explicitly and implicitly. So now I'll show you the implicit differentiation process, and we can see if we get the same result or not. So the point of implicit differentiation is to not have to isolate y. So we'll leave it as it is. If we take the derivative of both sides with respect to x, we'll put d dx on each side. That's taking the derivative of both sides with respect to x. And in the last video, we learned how to do these little pieces. So the derivative of y squared with respect to x is 2y to the first times the derivative of y because of the chain rule. So the derivative of y with respect to x is dy dx. And on the right side, we take the derivative of x with respect to x, which is 1. In this particular problem, we don't have to do any collecting of like terms because there are just two terms. At this point, we're just ready to isolate dy dx by dividing by 2y. So we get dy dx equals 1 over 2y. Now the question is that the same thing as what we got when we differentiated explicitly? Well, it doesn't look exactly the same. But if you remember, over here, when we isolated y is plus or minus the square root of x, or x to the 1/2. So I can replace in here the value of y with plus or minus x to the 1/2. And you can see now that this result is exactly the same thing as what we got explicitly. For a problem this basic, if you were asked to find dy dx, it's really your choice which of the two methods you want to use. It doesn't make a huge difference either way. However, we're going to see some more problems where isolating y is very difficult or impossible, and you're not going to want to do it explicitly. Let's take a look. In this example, you can see that y shows up in multiple places, and even if we remove the terms that have x's to the right side, still getting y by itself is kind of difficult, and we probably shouldn't even attempt it. Instead, let's find the derivative implicitly. And what that means is to take the original quantity and take the derivative of both sides with respect to x. As you get more comfortable, you may skip the line where you're showing that you're taking the derivative, but for now, showing it is a good indication of what you actually did. So now we take the derivative of each of the components the same way that we learned to do in the previous video. So the derivative with respect to x of y cubed is 3y squared, don't forget the chain rule, times the derivative of y with respect to x. That's all for the first term. Minus, and now we have to take the derivative of y with respect to x. By definition, that's dy dx. Then we take the derivative of 2x cubed. Noticing that x is the same variable as the independent variable, so we won't have to worry too much about the chain rule here. So the derivative of 2x cubed with respect to x is 6x squared. Minus, and then the derivative of x with respect to x is 1. Here's our equal sign. Now on the right side, we're taking the derivative of a constant. Remember that the derivative of a constant is always 0 because a constant, by definition, is something that doesn't change. So its rate of change is 0 because it doesn't change. In the case of taking the derivative of a number, it doesn't matter what the independent variable is. You can take the derivative with respect to x, y, q, any letter. The derivative of 8 will always be 0. So this new line that we got is called a differential equation. It's called a differential equation because it has differentials in it. The dy dx appears as part of the calculation. If you look back at the steps that we wrote down, the next step is to collect all the things that have dy dx on one side and all the things that don't have dy dx on the other side. So 3y squared dy dx minus dy dx. Those are the terms that have dy dx. Now the other two terms don't have dy dx, so we'll toss them over to the other side of the equation. So we'll get negative 6x squared plus 1. The purpose of having all of the terms with dy dx on one side is so that we can factor out dy dx from both of those terms. And what remains is 3y squared minus 1. The right-hand side stays the same. And the final step to isolate dy dx is to divide both sides by the quantity that it's being multiplied by, which is 3y squared minus 1. So we'll have negative 6x squared plus 1, and we'll divide by 3y squared minus 1. And that's the answer to dy dx. Notice that this expression for dy dx is in terms of both x and y. That's not something that happens when you take a derivative explicitly. But what this indicates is that the value of the slope of our relation depends not only on the x value, but on the y value as well. We'll apply that in some examples coming up later. Here's another example. This is another relationship between x and y that was given, and you may see that solving for y in this expression is not very friendly. So we'll just leave it how it is, except that maybe we'll change the square root into a 1/2 power. So we have x squared times y to the 1/2 equals x plus 2y cubed. Taking the derivative with respect to x of both sides, we now have to calculate the derivative of each side separately. We'll use the product rule to take the derivative of the left-hand side. So first we'll take the derivative of x squared with respect to x, which is 2x, and multiply by the second factor, which is y to the 1/2. And we'll add to that. This time we'll leave x squared the way it was and multiply by the derivative of the second factor, which is 1/2 y to the negative 1/2. Remember, you need to use the chain rule and multiply by the derivative of y with respect to x, which is dy dx. That's the end of the product rule for the left-hand side. For the right-hand side, we have a sum, so that one is a lot easier because we can take the derivative of the two pieces separately. The derivative of x with respect to x is 1, and the derivative of 2y cubed with respect to x is 6y squared times dy dx. Now we have to find all the terms that have dy dx. So those would be these two underlined in blue. And then all the terms that don't have dy dx, and these I underlined in green. So all the terms that have dy dx will go on the left. So we have 1/2 x squared y to the negative 1/2 dy dx. And we'll subtract the 6y squared dy dx to the left. And then all the terms that don't have dy dx, the 1 will stay where it was, and we'll subtract 2x y to the 1/2 to the right side. Since both terms on the left have a dy dx, we'll factor it out. And we'll be left with 1/2 x squared y to the negative 1/2 minus 6y squared. And the right side won't change for right now. And the final step to solve for dy dx is to divide by the stuff in pink. So we'll have 1 minus 2xy to the 1/2 divided by 1/2 x squared y to the negative 1/2 minus 6y squared. Now there are some algebraic manipulations we could do to help this look a little prettier, but for right now, let's leave it how it is. Here's an equation that's given that involves a quotient, y divided by x. If we start taking the derivative immediately, we're going to need the quotient rule to take the derivative of that first term. And that's fine. That is a totally acceptable way to do this problem. However, you do have the ability to manipulate the equation in some way if you feel it's going to make your life easier. You don't have to do this, but if you wanted to clear the fractions first before, you could avoid using the quotient rule. I'm going to do that just to show you what that would involve. So if I take the original expression and multiply both sides by x, that will force that denominator to cancel out. So the new expression will be y minus 2x to the 4th. Notice how the extra x didn't do anything too evil to the second term. It just raised the power by 1. Doesn't make it any harder. On the right side, though, we now have a product where we didn't before, but if you find it preferable to use product rule instead of quotient rule, then this was a good move to make. We'll put the letters in order. Now we can take the derivative of both sides. The derivative of y with respect to x is dy dx. The derivative of 2x to the 4th with respect to x is 8x to the 3rd. And the derivative of 4xy with respect to x requires the product rule. So we can leave 4x alone and multiply by the derivative of y, which is dy dx. And then next time, take the derivative of 4x with respect to x, which is 4, and leave y alone. Grouping the terms that have dy dx together. Dy dx on the left, and then the 4x dy dx will come to the left as a negative. And then on the right side, we'll still have our 4y that didn't move, and we'll add 8x cubed to the right. Factor dy dx from the left-hand side leaves you with 1. Be careful. A lot of people think that it just disappears, but factoring dy dx from dy dx leaves you with a 1 minus 4x. The right side doesn't change in this step. And the final step is to solve for dy dx by dividing by the factor next to it. So we'll get 4y plus 8x cubed divided by 1 minus 4x. Now, if you had done this problem the original way, without clearing that denominator x first, and you use the quotient rule, you will have gotten an expression that looks a bit different than this one, but it is equivalent and is possible to manipulate one into looking like the other. Here I brought in an example that has some transcendental functions in case it's been a minute since you've worked with them. It'll help you refresh your memory. We have natural log of x multiplied by sine of y, and it equals e to the 6th times e to the y power. Since the left side is a product, let's take the derivative of both sides. I won't spend the time writing d dx on both sides. Let's just jump in and do it. So we need to use the product rule to take the derivative of the left side. So the derivative of natural log of x is 1 over x, and we multiply by sine of y untouched, plus, and then this time we don't touch natural log of x, and we multiply by the derivative of sine of y, which is cosine of y. Now remember, we're finding the derivative with respect to x, so we have to take the derivative of y from the inside with respect to x. So we multiply by dy dx equals. Now the right side is also a product, so we'll use product rule again. So the derivative of x to the 6th is 6x to the 5th, and we'll leave e to the y alone. Plus, this time we'll leave x to the 6th alone, and we'll multiply by the derivative of e to the y. If you haven't seen that for a minute, you might remember that the derivative of e to the something is still e to the something times the derivative of that exponent. So we'll have e to the y times the derivative of y, which is dy dx. Underlining the terms that have dy dx, here's one, here's the other. Those are the ones that we want to have on the same side. If you're comfortable with it, you can factor out the dy dx in the same step. We'll be left with natural log of x cosine of y. That other blue term, when I subtract it, I'm going to have minus x to the 6th e to the y. And both of them will have dy dx, so I'll factor it out and write it on the left of the parentheses. On the right side, I'll still have 6x to the 5th e to the y, and I will have had to subtract sine of y over x. Just notice how I put this x down here in the denominator of sine of y. And your final step is to solve for dy dx by dividing. So we'll have 6x to the 5th e to the y minus sine of y over x. The whole thing divided by natural log of x cosine of y minus x to the 6th e to the y. Hopefully the process is starting to become more streamlined for you. Let's do one last example. This one has composition, and it has a tangent, and it has e to the something. In example 4, we chose to clear the denominator x to make our lives a little easier. Here, if you see that the square root is going to cause a bit of an extra problem, you could start the problem by squaring both sides. So if I square both sides of the equation, then I won't have to deal with the square root, but I will have to deal with the squared on the left-hand side. So we'll get x squared equals tangent of e to the y squared. You may feel that that is easier to take the derivative of than with the square root on the right side. So taking the derivative of both sides with respect to x, we get 2x equals. To take the derivative of the right side, you'll need to remember that the derivative of tangent of something is secant squared of that same something, of course using chain rule. So we'll have secant squared of the same argument, e to the y squared. But we have to use chain rule and remember to take the derivative of the piece that was nested inside the tangent function. So the derivative of e to the y squared is still e to the y squared, but we have to remember to take the derivative of the even more inside nested function, y squared. The derivative of y squared is 2y times the derivative of y itself, dy dx. That is an intense chain rule problem because this expression has many composition layers. If you think about the operations that happen to y got squared, then you raised e to that power, then you took the tangent of that result. The more operations you have in a certain order, that's how many layers your chain rule is going to have. The nice thing about this one is that we only have one dy dx. So solving for dy dx should just involve division by this other stuff. So we'll have dy dx equals 2x over all of this stuff. Let's see if we can clean it up a little. We'll have 2y e to the y squared and a secant squared e to the y squared down here. Just a little bit more that we could do to clean this up. We can cancel out these 2's. And we could also bring the secant squared to the top of the fraction as a cosine squared of e to the y squared instead of that secant. So writing it one more time nicely, dy dx is x cosine squared of e to the y squared over y e to the y squared, and that's it. Notice that all 6 of the examples I gave you here had very simple instructions. Find dy dx. That's all that was asked for. In the next video, I'm going to bring in a question that asks you to find dy dx, but then to use it to interpret things about the equation that was given to you. That's more of the type of questions that you'll find on the AP exam. So we'll see you in the next video. I hope you enjoyed this video. See you next time.